Good afternoon and welcome to today's HydroCAD webinar. Today's session is called All About Ponds, and we're going to attempt a fairly comprehensive look at ponds and what they are made of and what they're used for. My name is Peter Smart. I'm the developer of HydroCAD, and I'm going to be the presenter this afternoon. For folks who aren't able to attend the session, we are going to have a recording of the session posted later this afternoon, or if you want to look at the material again, then feel free to view that recording. You'll find that at hydrocad.net on our webinars page. So our goal today is to talk about ponds. And the first question is, what is a pond? As you probably know, there are four basic nodes that are available in a HydroCAD model: a subcatchment, a reach, a pond, and a link. So we're going to be talking about the pond. A pond is used for a number of different purposes, but primarily a pond is a volume that stores water. It's some kind of impoundment. This could be a reservoir, a dam, quite a large lake, or it could be something very small, like a catch basin or a concrete tank that's holding water. All of those are candidates to model as a pond. Another thing that characterizes most ponds is that they have an outlet device of some kind, and so we need to characterize their outflow capabilities, and this is done by setting up different kinds of outlet devices. The next basic element in any kind of pond is that we're routing a hydrograph through that pond. That is, we're taking a time-varying flow, typically a runoff hydrograph or some other hydrograph in our model, and we're going to route that hydrograph through the pond structure to see how much water is stored in the pond and what the outflow from the pond is at each point in time. So that's our hydrograph routing. We will also talk a little bit about some of the other calculations that pertain to ponds. That is things like our detention time calculation, how long is water resident in the pond, and how long is available for sediments to settle out or other contaminants to be neutralized. We're also going to talk a little bit about tailwater handling and coupled ponds, where one pond is creating a tailwater condition that affects or reduces the discharge from another. And then finally, we're going to talk a little bit about storm sewers, because storm sewers are commonly modeled in HydroCAD as a sequence of ponds where you have one pond flowing directly into the next, creating a tailwater for each pond in sequence. So that is the basic overview of the materials that we will be talking about today. So let's start by looking at pond storage. And I want to do that, first of all, by going through a couple of slides. Because of the limited time today, this will be a quicker way to get through some of this material. If you want further detail, either on pond storage or outlet devices, we do have earlier webinars we did, and you'll find those recordings posted, and that'll cover these materials in more detail. There are quite a number of different storage options that are available in HydroCAD for modeling pond storage. And basically, you're going to pick an option that most closely resembles the particular shape that you want to model. One of the most basics is a prismatoid storage, and you could use this for a tank or a rectangular vault, anything that's got basically four sides, either vertical or sloped. If you had something that is circular rather than rectangular in its plan view, then conic storage is a very popular option. And this could be used for a naturally graded pond, for a dry well, for a catch basin, various structures of that type. Pipe storage is used where we have a pipe. It could be a circular pipe, arch, elliptical, box, essentially any kind of pipe shape that we're storing water in. And this will apply when the pipe is essentially capped so that we're creating a level pool, a pond within that pipe. This would not apply if we're just using the pipe for conveyance. That would be a different kind of scenario. So pipe storage is strictly for situations where we know we have a level pool, where we have an outlet restriction that is relatively small in relation to the diameter of the pipe, such that that pool is able to form. And then we have custom storage. And custom storage is used where you have measured information such as contour elevations, where You can measure the surface area at each contour elevation and use that data in order to define the storage of the pond. And this is often used for natural graded ponds, dams, reservoirs, things of that nature. In addition to these standard shapes which are typically used for above ground storage, HydroCAD is also able to model underground storage. And you can use any of the standard shapes, but more commonly you're using some kind of chamber product in order to model that underground storage. And these could consist of sets of chambers. There are milk crate type chambers. Those would be relatively easy to model because you could use the prismatoid option and simply specify the voids, that it is 90 to 97% of that total volume is available for storage. So those are fairly easy to do. But it gets more involved if you have something like pipe storage, where you have a much more complex stage storage relationship, and the pipe may even be sloped to complicate things even further. We also accommodate plastic injection molded stormwater chambers, and these products have a special geometry which doesn't readily match any of the standard storage shapes, and so for that reason we have a library of chamber definitions which are built into HydroCAD. And this allows you to simply pick the appropriate model of chamber, and the stage storage relationship is known for each of those models. Chambers are typically used in some arrangement, some configuration with multiple rows of chambers. They're also usually embedded in stone, which is part of the structure of the system and also contributes to some of the storage due to the voids in the stone. When you set up the embedded chambers in HydroCAD, it automatically handles the embedding calculation, removing the volume of the chamber from the surrounding stone, but also adding in storage for the voids in the stone's surround. There is also a storage multiplier which is present in all the storage definitions in HydroCAD, and this is particularly useful when you're setting up chambers because you can specify how many chambers you have rather than having to put in 2 or 20 separate chamber definitions. The voids allows you to specify the amount of space that's available between your backfill. So if you had a clean angular stone, you might have as much as 40% voids. If it were sand, it might only be 20%. And this can be used either for the fill around chambers or even for a structure that you might completely fill with stone. Perhaps even a gravel-filled trench would be an example of a situation where you would have a pond volume and where you would specify the voids. Based on all of this information, HydroCAD calculates a final stage storage curve for the pond. And this example shows you what's happening when you set up an underground storage system. That we actually have the chambers that are occupying this middle storage range here. Underneath the chambers we have a stone base, so we have a linear increase in storage down the bottom when we're just filling the voids in the stone. Then the amount of storage increases more rapidly while the chambers are filling with water. Then once the chambers are completely filled, in this example we may not have any additional storage. That's what's being shown here. We may have an impervious layer on top of the chambers. And then we might actually have some additional storage above grade. So if this storage chamber system is underneath a parking lot, then when the chambers fill and the connecting catch basin fills up, we may actually start storing water in the parking lot above the system, perhaps in the 100-year event. So all of that information is combined by HydroCAD in order to create the overall stage storage curve for that pond. The underground storage wizard or the chamber wizard makes it very easy to set up these underground systems. We can basically just pick the specific model of chamber and set the layout, the length of each row, the number of rows, and based upon the manufacturer's typical spacing, cover, and bedding, it will automatically lay out a system and do the storage calculations for that system. Most underground detention systems will also have an infiltration component or exfiltration where you're intentionally leaching water into the surrounding ground, and that's typically modeled by setting up an exfiltration outlet on the pond. That gets us into outlet devices, of course. And stormwater chambers can be of many different kinds, plastic chambers, concrete chambers, and you'll find all of these in the HydroCAD chamber library. For each pond you set up, keep in mind that you can have any number of different storage definitions, what we refer to as compound storage. And underground storage is one scenario, but even for above grade storage, it might be that you have a couple of different storage definitions. As long as each of those storage volumes is connected such that the water will equalize in between them, then they can be considered to be a single level pool. So as long as that you have that connection between them, either through perforated pipe or a connection between two vaults, then we can treat those as a single storage volume and put them in as, or a single pond rather, and put them in as multiple lines within the pond storage definition. Another very important aspect of modeling any kind of pond is to make sure you deal with any overflow situation. And by overflow, we're not just referring here to the water that may flow over a weir or a spillway, but to make sure that we have defined enough storage to avoid a pressurized situation. So for example, if you do have a weir outlet on a pond, you actually need to define storage to some point slightly above the crest of that weir. If you don't do that, then the storage stops at the point that you tell it to. So if you only go to the spillway, you don't have any storage above the spillway. And then when the water is 1 inch over the spillway and actually the spillway is actually operating, the software doesn't know how much storage is in that 1 inch. That 1 inch might have 10 cubic feet or it might be 10 acre feet. So it's very important to know what the storage is. So in general, the key is to define your storage to some distance above your highest outlet device. You will get a warning message from the software when you do the routing if your storage does not go high enough. So you'll want to check that message and make sure that you define that additional storage. When you do this, you're not setting up fake storage. This is very real storage that you're providing. And so it's going to be the actual volume of water that is occupied by the water at any given elevation. Exfiltration in HydroCAD has several different options. You can set it up in order to model through the bottom and the sides of a given area, or you can model just to go through the bottom. You can also define a constant exfiltration as a CFS rate if you prefer to do it that way. You can also set up an invert elevation for your exfiltration, which allows you to prevent elevation or exfiltration from happening through the lower reaches of a pond. So there are quite a number of options for exfiltration. And I am jumping ahead a little bit because technically exfiltration is treated as an outlet control device, but here where it's often being calculated over the storage volume that you're specifying, so the two elements do relate. And so we have options for setting up our exfiltration based on either the surface area or the wetted area of the pond. Essentially, calculating on wetted area allows us to have exfiltration applied through the sides of the pond, whereas when we use surface area, the exfiltration is only going to be downward. And then again, in both cases, we have the option to set up an invert elevation in order to prevent exfiltration through the bottom of the pond. Okay, that's a quick overview for pond storage. Let's have a look at a couple of those options in HydroCAD. And to do this, first of all, let me just pull up a chamber example, which is pre-installed in HydroCAD, and just sort of jump to the end here to show you some of the fun stuff. This is a pond in which we've used the chamber wizard in order to model underground storage. And when we click the wizard tab, we get a special report on the wizard report, which shows us the actual layout of the system. And we could just simply click edit and come into the pond definition. And when we have used the wizard to set up pond storage, then we automatically have two storage definitions here, the outer storage field and then the embedded chambers. And if we edit either one of those by double-clicking that item, HydroCAD opens up the chamber wizard. And this is where we are able to select the specific chamber that we want to use within that system. and then we can tell the software to use the typical manufacturer's layout, spacing, cover, embedding, and if we wanted to, we could uncheck that and we could adjust those parameters for the system. And of course, we can adjust the number of rows in the system and the number of chambers per row until we achieve the desired storage and other characteristics for the storage system. So that's how quick and easy it is with the Chamber Wizard to set up these situations. I've just made a change there. I've changed the chamber model and changed the layout, and the whole model's been recalculated with that revised information. It's that fast. Now, most of your storage definitions, let's come back into the edit screen here, are going to be done manually. So when you edit our pond, you will go to the storage tab where we have our list of storage definitions, and on a new pond, and let me do that. Let me just close out of this and let's create a brand new pond. So coming back to our open project, we'll come to the palette, drag a pond into this project. And when we double click that, because it's a new pond, it will open up the editing screen for us. On the editing screen, we need to choose first of all whether we're going to have any storage in this pond. The catch basin option is used for a zero storage pond, essentially a pond that's so small that we want to neglect the storage as far as the routing calculation. And the benefit of doing this is we get a much more stable routing if we don't attempt to route through 10 cubic feet of storage in a catch basin. So that's where that option comes in. In this case, we're talking about storage definitions, so we would be selecting the detention pond option. And when I pick this, you'll notice that the storage tab appears at the top of the screen. So now, selecting the storage tab, we have a blank list in which we can enter the storage definitions for this particular pond. So we can select any line on this table, one line for each storage definition, and click Edit Storage, or we can simply double-click a line. When it's a new line, we have the option to select which storage definition we want to use for that particular storage volume within the pond. So we might pick prismatoid, for example, and within this we can specify an invert elevation, a bottom width, length, height, and a side slope if we prefer. Each of the screens also has an option to set embedding, and this is used when we're embedding chambers, typically within a stone bed. The voids can also be specified, and the voids should only be set when you're defining that outer volume that's filled with stone. The embedded chamber itself is going to be 100% voids, typically. The entire inside of that chamber is empty and open, available for water storage, so its voids should be 100%. And then storage multiplier can be set if we had multiple volumes set up that are identical, same dimensions and same invert. You'll find that these parameters, the right-hand side of this screen, are common to pretty much all of the outlet devices. You'll find those available regardless of the particular geometry or option you select. So when we click OK, we have a prismatoid defined. We could now continue to another line on the storage table, and we might have some above-grade storage defined as a vertical cone or cylinder. We might put that up at 110 feet and make it 2 feet deep with a certain side Z. And now we have two definitions that are set up in that pond. So we can continue this process with as many storage definitions as we want within the pond. We can click OK when we're done. We now have a pond that has only storage definitions. We haven't put any outlet devices in it yet. And in fact, we don't even have any inflow. But we can now double-click that to open up a report window. And the hydrograph plot is empty because there is no flow. Discharge is 0 at all elevations because we have no outlet devices. But on the storage tab, we do in fact have storage. So here we have the storage from our prismatoid, which we set at an elevation of 100 feet. So we have prismatoid storage over this range, and then this vertical cone cylinder that we put in this quick example to represent some above-grade storage. So this might be a tank of some kind that then overflows into a parking lot above grade. So that's the basic quick idea for how you would set up the storage. And I'm not going to spend further time on each of the storage definitions at the moment. I would urge you on each of those to use the help system. So if we come back into the storage tab, and if we have a question about which one to pick here, then we could just click help on this box, and the help system will give you some illustrations and a brief discussion of each of the storage options. You can click the links there for further detail and it'll provide exact information. Once we're editing a specific storage definition, then of course we can click the help button right there and we'll get even more specific help. If you need more information, you will also find details on our website. If you go to hydrocad.net on the support page, there's quite a bit of discussion there on pond storage and the different options that are available to you. Okay, I want to move on now to pond outlet controls. This is the next general category of elements that we have in a pond definition. And there's a whole range of different outlet options that are available in HydroCAD, and these range from a basic orifice of different shapes, different kinds of weirs. We can also handle low head conditions where we may have weir flow occurring as opposed to orifice flow, and we can handle culvert flow, looking at not only inlet conditions but also tailwater scenarios, and we can look at exfiltration, that is the leaching of water out of a pond into the surrounding ground. And we even have a special outlet capability which you can use to model pumps or custom stage discharge relationships or other things of that nature. So there's quite a range of different options there in the pond outlets. Let's just have a look at a couple of those. So, for example, looking at weirs, it's useful to look at some of the different ways you can construct a weir shape. There are basic options for a rectangular weir and for a V-notch weir. Those are two of the more basic ones. A trapezoidal weir is essentially the same as a V-notch weir, except that the crest length is non-zero. Or put it in another way, the V-notch weir is a trapezoidal weir with a zero crest. So that's essentially how you can choose between these. Now, if you have a more complex shape, such as a notch that's cut into a spillway, then there are a couple of different ways we can approach that. One is that we can essentially superimpose standard outlet devices. So we could take a rectangular weir, and then we could take a trapezoidal weir and notch that into the rectangular weir. And we'll do that by setting a weir rise parameter. And the rise parameter is that dashed line, which indicates how high that trapezoidal weir should be before the trapezoidal portion stops and the rectangular portion begins. We'll look at that in HydroCAD in just a moment. But another way you could model that situation would be with a custom weir and orifice. This outlet option actually lets you specify the width of your outlet device at various elevations. So this essentially lets you draw this outlet device. So you can provide essentially the same kind of outlet structure in at least two different ways here. The custom outlet also has the ability to let you define multiple openings in the one outlet device. And that can be very handy. For example, if you have something like a baffle in the bottom of a catch basin, which is forming a weir when the water spills over it, that you also have water going through an opening or an orifice in the baffle. In order to structure the outlet device routing properly, it's very useful to be able to use a single outlet device, in this case the custom weir orifice, and have that one device define both the orifice and the weir over the top. And then you can also have submerged weirs. Basically any of these standard geometries can be submerged. There's a weir submergence equation that HydroCAD uses in order to look at the tailwater at each step in time and determine what reduction in flow is appropriate based upon that tailwater. And of course this is a web page off of the support section of our website, so you can go in here and find the particular information you're looking for, discussing various outlet devices. There are separate articles here on these compound weirs, which I've just been talking about, and also discussion on broad crested weirs. And let me touch on that briefly while we're here. The primary difference between a broad crested and a sharp crested weir, as far as HydroCAD is concerned, is that a sharp crested weir has a constant weir discharge coefficient, a constant C value, regardless of the head, regardless of the water depth over the weir. A broad crested weir is modeled differently in that the coefficient is allowed to vary depending on the head. And depending on the shape of the weir, that coefficient variation may be significant. In other cases, however, it may not vary greatly. But the underlying weir equation is essentially the same in the two cases. So If you are considering using a broad crested weir, then one of the things you want to look at is whether or not there's a significant variation in the weir coefficient that you feel you need to represent in the model. In many cases, you may find that those variations in the coefficient don't have a great effect on the final hydrograph routing. So I'd urge you to do a quick sensitivity analysis when you're looking at those situations in order to decide whether or not you need the additional complexity of a broad crested weir or whether you can just use a standard sharp crested weir, which also, by the way, gives you a broader range of geometry options, such as the V and the trapezoidal. The broad-crested weir is only available to you in a simple rectangular crest, as shown in this example. And that's because we only have good test data for these kinds of rectangular weirs. Okay, let's go into HydroCAD for a minute and just have a look at a couple of these different weirs or outlet devices. And this is actually a pump example. Let's just set that aside for a moment and just bring a new pond in here for this example and double click the pond. Now in this situation where we're going to set up outlet devices, we could use either the catch basin or the detention pond option. Both of those options give us an outlets tab up top. In this situation, I'm just going to pick the catch basin option because we don't need storage right now. We could come back later and actually change this from catch basin to detention pond if we wanted to, and we could add a storage definition to it. But right now we'll go with the catch basin option and then go up to the outlets tab. And this gives us a blank table, very much like the table we had a moment ago for the storage volume definitions. Each line can be used for a separate outlet device, and we can have as many outlet devices as we need within that pond. So if we double-click a blank line within that table, or we could have used the Edit Outlet button, they'll both bring us to the same place, we get a list that gives us all of the available outlet devices. And so we can choose here, for example, let's take a V trapezoidal weir and click OK. And we can here enter the parameters for our weir, such as the invert elevation, which is the crest elevation. If we had multiple devices, perhaps this is multiple notches within a spillway, then we could set a discharge multiplier. Otherwise, we'd leave that at the default of 1. And then we can set a notch angle. And the notch angle is the total included angle between the two sides of the weir, be it V or trapezoidal. If you have questions about this, do click the Help button and come in and have a look at the weir calculations, and you'll see that the notch angle is in fact displayed here, so you can understand exactly how those parameters are defined. So we could put in a notch angle, and based on the notch angle, a weir coefficient is calculated. You could change this coefficient if you want to, so this is just a recommended default. Again, the help system will explain how that calculation is being done. And then if this were a trapezoidal weir, we could specify a crest length. If it were V, just a V notch, the crest length would be 0. So let's put in 2 feet for a crest. And then finally we have the rise. The rise is this parameter I mentioned that allows us to essentially specify how far high this weir is. And we would use this in a case such as a notch cut into a spillway. So if the notch was 2 feet high, then we would have a rise of 2 feet. So the notch would be cut that 2 feet in to the spillway. And so here let's actually set this up as a couple of notches. So let's set the discharge multiplier at 4 for 4 notches, and let's make them a 1 foot horizontal crest and 1 foot high. And I've set the bottom of each of these notches at 100 feet. So I'm going to change the name here and just call this a notch. And then we want to set up the actual rectangular spillway that we are notching into. We could do these in either order. And I'm going to use a sharp crested rectangular weir for this situation. And the spillway here is going to be at 101 because the notch was at 100 and it's a foot high. So the spillway on the main rectangular crest is at 100 feet, and we would specify a crest length. The crest height is the distance above the approach channel, and again you can go to Help for details on this. This affects the discharge coefficient, which is used for the weir, and you can leave that blank if you don't want to apply that automatic adjustment. The weir rise is also available on this screen, and we could use it here. For example, if we had a couple of different width rectangular weirs, then we could use the rise to specify the height of each portion. If we leave the rise blank, it assumes that this outlet device can support an infinite height, so the water can go as high as it needs to, and the same geometry will be maintained. So we click OK a couple of times, and we've entered our outlet devices for this pond. And now double-clicking the pond, we again have no inflow or outflow hydrograph, but we do have a stage discharge curve. And this curve is showing us on the left axis, as the water gets deeper here from 100 feet up to 101, we have flow occurring through the notch. Now, up at 101 is where we set our sharp crested weir, and you'll notice our curve isn't continuing beyond that, so we're not actually seeing the behavior of that crest. So we need to expand the range of this graph. If we had defined storage, then that would be one thing that would automatically expand the range. But another trick you can use, if we edit the pond and go to the Advanced tab, we can set a flood elevation. And normally this is just the elevation at which we get a warning message that we've exceeded a certain level. But here we could put in 102 for our flood elevation and click OK. And now we've expanded our elevation range so it goes up to 102. And particularly if I flip this graph to a 2D view, you can now see that we have this smaller increase in storage versus depth due to the notches. And then when we hit the sharp-crested rectangular weir, we have a much more rapid increase because of the larger surface area. So it's just an illustration of two outlet devices used together and using the rise capability in order to limit the height of one of those devices. Essentially what we're doing is we're preventing the overlap between the notch down below and the broader rectangular weir up above. If we did not put that rise in, it would treat this as if the notch were completely separate of the rectangular weir and that it continued with no restriction on its height. We can also do these kinds of things, as I've mentioned, with a custom weir and outlet device. Coming back to our Outlets tab, the custom weir and orifice essentially lets us draw any kind of outlet. And you'll find detailed examples in the help system, but essentially the way you could set this up, let me see if I can do something similar. We'll go to 100 feet, which is where our notch started, and if we're 1 foot wide at 100, and then we come up to 101, and we would need to work out the width of that point. Let's say it's 3 feet. So as we go, it draws that portion of the outlet device. So we now have a notch, a single notch, at that particular height. And then if we wanted to enlarge this into a broader spillway, we'd stay at the same elevation of 101, but specify that that rectangular spillway is going to be perhaps 10 feet wide. Now let me come up another foot and the illustration will be even a little bit clearer. So now you can see how we've created a notch and then expanded that up to a rectangular weir above that point. And then we can go as high as we need to. We do want to make sure, if this is an open-topped weir, then we want to make sure we come high enough with this illustration in order to handle whatever routing levels may happen during the actual hydrograph routing through the pond. So that's a quick example, and help will give you some more details, such as an orifice set below a weir, which you might use in a baffle situation within a catch basin. So there are a couple of different ways that you can model these custom outlets, either by stacking outlet devices side by side, or one on top of each other rather, or by using the custom weir and orifice. They will both give you essentially the same result. Let's look just briefly at a couple of other outlet devices. Actually, let's look at compound outlets, which is one of the more confusing aspects. If you have a culvert outlet on a pond, and let me set up a new pond here. If we have a pond with simply a culvert outlet, that's fairly straightforward. We just go to the culvert screen and click OK and put in our inlet and outlet elevations, our length, slope, Manning's number. I'm just quickly putting values in here to move us along. And finally a diameter. So now we have a culvert coming out of a pond, and we can double-click that to get a staged discharge curve. And again, we could use the trick of going to the Advanced tab and setting a flood elevation in order to kick that range up higher. So now we can see the relationship for pipe flow with a slight decrease in flow when the pipe becomes completely filled, and then pressure flow occurring beyond that. So a culvert's a fairly common and simple kind of outlet on a pond, but a riser structure is also used very often where we want to in some way limit the flow that's coming into that culvert. And we would set up a riser as a compound outlet. So we would go back to the Outlets tab for that particular pond. We'd typically want to put our culvert in first, being routed to primary. That's the primary discharge that's routed on your diagram. And we would now build the riser structure above that. And riser structures are typically a pipe section or concrete vertical riser. And what we need to model is not only the culvert barrel coming out of that riser, but we also have the flow that's coming in through side openings and flow that's coming in through the top of the riser. So we would just set those up by starting with the culvert barrel and then working up into the body of the pond. So we'd set up the culvert first, as I've already done, with an invert at 100. And then we might put an orifice in the side of the riser structure, perhaps up at 102 feet. And we can specify that the orifice is either in a horizontal or vertical plane. This will be a vertical plane because we're cutting a hole in the vertical side of the riser. And let's say it's 4 inches in diameter, and we could specify that we have 4 of these openings that are spread around. And actually, I want to set that. Here's a discharge multiplier of 4. And now what I've done is I have a culvert outlet and an orifice outlet, but they're independent outlets as they're currently set up. What I skipped here is that we need to change the routing. And the important thing here is how we read this table. This first line, the culvert, is outlet device number 1. That's what that 1 is in the first column. So our culvert is device 1, and it's routed to the primary discharge. Device number 2 is our orifice / grate, and it's currently routed to primary, and that's what I need to correct. So we need to edit that, and what we want to do is change the routing, and we want to route the orifice flow through it so it goes through device 1, which is our culvert. And so now the water will come through the orifice and then flow through the culvert. That's how we get the compound behavior. Now we also need the top of the riser, so we could again go to an orifice / grate, and let's come up to 105 perhaps for the top of the riser. And this needs to be a horizontal plane, perhaps a 36-inch diameter, and we have to set the routing. And again, we're going to route this to device 1, device 1 being the culvert here at the top of that table. So what will happen is the water will go through the top of the riser and through the side openings and be combined and go through the culvert barrel. And let's click our flood elevation up here a little higher, maybe 106, and click OK. And now we can see the combined behavior of this riser structure. We still have our culvert barrel down the bottom at an invert of 100 feet, but we're not getting any flow at that point until we get up to the orifice openings that are in the side of the riser. At that stage, we start to get flow through the orifice. Then when we finally get to the very top of the riser structure, we get an increase in flow as we start to get a very substantial weir flow over the top. And then at some higher point up in here, we're actually seeing another point of inflection where our culvert barrel is actually starting to control. So we have so much water going over this 36-inch riser that this 12-inch culvert can't handle it. So at this point, we start to limit the flow based on the culvert. So that's a quick example of setting up a compound outlet, but that's a very common scenario, setting up a riser. Okay, let's move on now to pond routing calculations. I know there's a lot more about pond outlet devices that you might be interested in. We did do a previous webinar specifically on outlet devices, so I would urge you to go back and have a look at that recorded session if you want more information. And that goes through each of the outlet devices in considerable detail, including each of their parameters. So for a routing example, let me just close out of these couple of projects I have open here. And let's have a look now at a couple of relatively simple pond setups. But I want to start by looking at what happens when we actually route a hydrograph through a pond. So what I have in this scenario is I have a simple runoff area. It could be, of course, an entire complex watershed and stormwater management system, but in this case it's just one subcatchment running into a detention pond. In this case it's a tentative wetland. The exact details of the storage don't matter at this stage. What I want to do is I want to look at the reports and the hydrograph that goes through this system. So if I double click this, since we already have data entered for the pond, it will open up a report window. So it automatically calculates all the inflow to this point and routes it through the pond. The default report we get is the hydrograph, and this shows us the inflow and outflow hydrograph, so the flow versus time. We can toggle this, of course, between a 2D and a 3D view, and you can also zoom in more closely by dragging from an upper left point to a lower right. And this drags a selection rectangle and lets you zoom in successively on a closer point on the graph. And you would just drag in the reverse direction from lower right to upper left in order to reset the zoom to the original view. Now, one of the most common characteristics of any pond routing is that we get this reduction in flow, this peak attenuation. So we have started with an inflow of about 32 CFS, and because of the storage and restricted outlet in this pond, that's been reduced to about 12 CFS. You'll find, in addition to a few pieces of critical information that are called out here, if we go to the Summary tab, we'll get much more detail on that particular pond. And I'd encourage you to look at the summary report for each of your nodes, not just ponds, but all of them, in detail, and make sure you understand everything that's shown on the summary. The summary is a compilation not only of the routing results, but also all of the data that you've entered for this pond. And if you're getting results that are not quite what you expect, then probably it would be revealed somewhere on this report. For example, you can come in here and you can look at each of your outlet devices and you can see exactly what parameters you've used for the culvert. In this case, we have a culvert outlet and then simply a spillway up top. Check your invert elevations, make sure those are what you expect. Similarly, all of your pond storage definitions are listed here. In this case, we have custom storage, which is shown in the table below. And then at the very top of the report, we have the routing summary. So we have the peak inflow coming into this particular subcatchment, into this pond, the time at which the peak occurs, and the total volume of the inflow. And then we have the outflow, which has been reduced by a certain amount, and it's being reduced by 61%. That's the peak attenuation that's occurring. And the time of the peak has also been delayed. There's a time lag of 82 minutes, so our outflow is peaking 82 minutes after our inflow peaks. And then the outflow may also consist of several components. We might have a primary, secondary, tertiary, even discarded flow. Those will all be listed below. In this case, we have only a primary outflow, so you'll notice that the outflow, the total outflow, and the primary values are the same. Below this is the routing method that was used to do this hydrograph routing, the time span over which the calculations were performed, and the time step which is used for those calculations. We then have a peak elevation, the time at which it occurred, the surface area at that peak elevation, and the storage that occurred at that same point. Down the very bottom of the report is a device analysis summary. And this is designed to help you break down the flow. So in this scenario, we had a total outflow of about 12 CFS. And coming down to the bottom, here's our 12 CFS. And we can see that some of that was through the culvert, about 4 CFS, and about 8 CFS was coming from the weir. So this helps us apportion the flow, the peak flow through that device. You will notice that the flow down the bottom here may sometimes differ from this flow up top, and we have a slight difference here. This is to be expected, and there are several reasons. One is that this flow at the bottom is a maximum flow, whereas the flow at the top is a peak. The peak flow is interpolated between the highest 3 points in the hydrograph, whereas the maximum is the highest single point that occurs during the routing. This calculation may also be different because it's using the headwater and tailwater elevations that occurred at that closest time step in order to do this analysis. If you use smaller time steps, then you can reduce the differences between these two. But just so you know that those results can be different, and that's normal. If you don't want to explain that to a reviewer or someone else looking at your reports, then you do have an option to right-click and go to Report Items, and you can deselect Device Flows, and it will remove that detailed analysis from the report if you'd prefer not to see that. A couple of other notes about hydrograph routing and understanding the results. If we go to the hydrograph, as I mentioned a moment ago, this is the peak discharge, which is labeled on the curve. If we go to the tabular view for the outflow, we get the individual flows at each point in time. And you'll notice here that we actually have multiple values, two values here that are shown in bold. Here we have just one value. One value means that is the highest single value that occurred in the table. Two values means, in bold, means that the highest value actually falls in between the two. And what we need to do is we need to come over here on the right and unshrink this table by popping up the shrink button. When we do that, then intermediate values are displayed, and now there's just a single value in bold. It's telling us that now it is showing us the highest maximum value. But again, this is at that particular time step, this 3.31.92, the interpolated peak flow in this particular scenario is reported as the same. But often that interpolated peak will be slightly higher than the maximum value at the closest time step. So just something to be aware of. Stage discharge report we've looked at briefly, and of course these are available in tabular form as well, and they also operate with the shrink button that lets us adjust the size of this table. And then the stage storage relationship. Here, because we entered surface area to define our storage, we're getting a gray curve for surface area in addition to the blue curve showing the storage. Other important things to look at in our pond report is a detention time. The detention time is a measure of how long the water is resident in the pond, and this is calculated by two procedures, the plug flow method and the center of mass method. These procedures are different numerically, and there is detail on our website about how these are calculated. The center of mass method simply finds the center of mass of the inflow and the outflow hydrograph and takes the time difference between them. So it's relatively simple once you know that center of mass time. The plug flow procedure actually divides the inflow and outflow into plugs of equal volume and calculates the time between a given plug entering and leaving the pond and averages the time for all of those plugs. So the two procedures are a little bit different. They will sometimes produce very similar numbers. Other times the numbers may be somewhat different. The center of mass method is a simplified procedure, and so it may not accommodate certain situations such as water retained in a pond. For example, in this scenario, where actually our time span doesn't go long enough for the entire pond to empty. You'll notice we've still got discharge at the 30-hour mark. And that's why the plug flow information indicates that it's using only 85% of the inflow in order to calculate that value. So if we were to go to our calculation settings and increase our time span, perhaps out to 60 hours, now it's using 100% of the inflow, and you will notice that the results of the two methods are now essentially identical. They're within 1%. So in the textbook case, the two are the same, but the plug flow method has the ability to give you meaningful results for other calculations, such as water retained in a pond, a wet pond, for example. Okay, the one tab we haven't looked at here on the pond report window is the sizing tab. We've looked at how you would define storage for a pond, but not the question of how you determine how much storage you need. When you're designing a pond for peak attenuation, the sizing report is very handy for that. And what you would typically do to get there is that we would usually model our existing scenario first, use that to determine the peak discharge from our site. And typically that is all you're allowed in the developed scenario, or perhaps you're allowed 110% or 90% of that. Whatever it might be, you'd use the existing scenario to determine your permitted discharge. You would then go to a model for your proposed situation with your proposed watershed, and you'd generate the runoff hydrograph from that proposed watershed. You'd then take a new pond. It doesn't need any description in it, just a pond node. You'd run your proposed runoff into the pond, and then we need to right-click that pond because there's no description yet, and force it to open a node report. So we have a pond with no storage, no outlet devices, so the hydrograph's just passing straight through it. And that's not very interesting. But if we come to the sizing tab, the sizing tab allows us to estimate how much storage we would need in this pond in order to attenuate this actual proposed flow to the target level. So what we would do, if we flip this to 2D view, which is a little easier to read, is that we would come over to the left side of the graph and we would look up our target flow. So if we were being allowed, for example, to discharge 14 CFS, if that was our pre-development flow, we'd come across from the 14 mark to the curve, and then we'd come down to the bottom axis, and that would tell us that we need about 2.7 acre feet in order to detain this actual inflow of about 32 CFS and knock it down to this target of 14. So we would use this as an initial estimate for designing the storage of our pond. Then once we've set up the storage and the suitable outlet devices, then we would use an actual hydrograph routing in order to determine the pond's behavior and fine-tune the storage and outlets until we got the exact behavior that we were looking for. So that's the role of the sizing report, is just to do that initial sizing calculation. Once you've set up a pond, then you would use an iterative process in order to adjust the storage until you get the exact behavior that you're looking for. Okay, again, detailed articles you will find on each of these topics on our website. There is a separate article specifically on the pond sizing report that explains how it works and how to use it. Okay, now I want to talk a little bit about very important items, usually left for the end, of tailwater and storm sewers. Everything we've been looking at so far entails isolated ponds that have a free discharge scenario. But in many cases, we're going to have tailwater conditions that are limiting that flow. So let me just get back to this clean project. And what I want to look at here is a single subcatchment for simplicity, which is running into a pond, tentatively a wetland in this case, but essentially a pond. And let's double-click this to open the report window. So we have an inflow and an outflow hydrograph, as we did a moment ago. Simple enough. Now, let's say, closing that for a moment, let's say that this one wetland is going to discharge into another wetland downstream. So we could create another pond for the downstream point and run that flow into it. But actually I'm going to do another little trick here just to show you. Let's say that this downstream pond is going to be very similar to the upstream pond. We could right-click this upper pond and do a copy, and then we could do a paste in order to bring in a complete copy of that node. We can also do the same thing by doing a control drag on that node, and that brings in an exact clone of the node. We can now take the upper flow and route it to the lower one. So now I have two absolutely identical ponds. They're at the same elevation. So the lower one presumably is going to fill up and create some kind of tailwater issues on the pond downstream. Let me just make sure I have a setting right here. I actually want to change this back. Your default routing method is the storage indication method. This is a static routing method that is not tailwater sensitive. But I suggest you start with that default. And when you route through a single pond, let's double-click for report window. There are no warning messages down here in the box. Everything looks just fine. But if we take the flow down into this lower pond, so two identical ponds, and now open a report window down below, let me pick one of our storms, 25-year storm, you notice we've now got a red warning message that's occurring. It's telling us that 7P, which is this lower pond, has exceeded the water surface elevation in 1P. And it shows us the maximum amount by which it's exceeded and the time at which it occurs. So this message is telling us we have a tailwater condition that is not being handled. That's why it's a red warning. If we click that warning message, we'll get detailed information. And essentially what the message is telling us is we need to change the pond routing method. So we need to use a different routing method that is able to handle tailwater. So if we come to our calculation settings screen, and usually we will simply be changing the pond routing from storage indication to dynamic storage indication. SimRoute is a more complex procedure for limited situations such as reversing flows. You'll want to read up on that more before you use it. For most situations where you have tailwater, dynamic storage indication is what's recommended. So now if we click OK, the calculations have been updated, and you'll notice our red warning has disappeared. So the software using the dynamic storage indication method has now been able to reduce the flow from 1p down to 7p based on that tailwater. Now, to have a look at this, let's just this is the report window for the lower pond. Let me close that. Let me open up the report window upstream and switch to 2D. And now what we can do is we can watch that report as I remove the tailwater condition. So what I'm going to do is I'm going to take this, let me move these aside a little more so you can see better. I'm going to take this outflow and remove it. And when I let go of that, you'll see a change occurred in this portion of the outflow hydrograph. In this particular situation, the tailwater condition, and I'll reconnect it now, the tailwater condition is not affecting our peak discharge, but it does have a significant effect on how the pond is drawing down. So that's just a quick illustration to show you that you will get warning messages when a tailwater occurs, and that changing the routing procedure will allow you to accommodate those conditions. The next and final item I want to touch on are storm sewers. Storm sewers are essentially modeled as a series of catch basins. A catch basin is basically a very small pond. It's a pond where we have so little storage that we're actually not going to describe the storage to the software. Instead, we're just going to say this is a zero storage pond. The storage here is insignificant. So what we want to do is simply look at the outlet controls and determine what head, what hydraulic grade line will exist in the catch basin. What head is necessary in order to push a given flow out through that particular pond. So to set up one of these quickly from scratch, if we bring in a new pond and select the catch basin option, and then down at an invert of 100 feet, I'm going to put a culvert. And let's have this drop 1 foot over 50 feet. And just quickly pick an entrance loss here, and we'll make this a 12-inch culvert. And so we have a pond which has just got a culvert outlet. There's nothing else in it. And let's run this runoff hydrograph into the pond. Double-click for report. Now, because we have no storage in this pond, the outflow is always going to be equal to the inflow. The only way we can get a change in flow is by storing some water and detaining it. So Q out is guaranteed to be equal to Q in these situations. But the report will tell us what the peak elevation is here. So we have a peak elevation that's occurring of 102.53. So that's the head that was necessary in order to push this 3.19 CFS through this culvert outlet. Now, over in our message window, we do have a hint that's appeared. It says this pond has peaked at 102.53, flood elevation advised. What it's telling us here is that it's calculated how high the water will get. The question is that overflowing a grate and flooding a parking lot? What does that mean? So what we would typically do when we're modeling a catch basin is to go back, edit that pond, go to the Advanced tab, and here set up a flood elevation typically to the rim or the grate of that catch basin. Essentially the point at which that catch basin is going to start to spill over or perhaps pond and form a pool in a parking lot above, we would want to specify that level, at least for warning purposes. So let's put in 104 for the moment, click OK. And now our hint is gone. We haven't changed our routing results, but this is telling us that we are less than that flood elevation that we've specified. So we have one very simple catch basin here, basically just a culvert and a rim elevation. Now if we had another catch basin in the system, we could use that old trick of a controlled drag in order to make a copy. So we have a second catch basin, absolutely identical to the first one. So it's at the same height. The pipe is sloped. Now obviously you would usually set that next catch basin a little bit lower, but in this case the two are the same. And let's route the flow from the first one to the second. And then let's double click that second one to get results. And now we are getting a message that the lower one is actually above the flood elevation. Let me just check my routing method here for a second. We're on dynamic storage. What I wanted to do actually is go back to the default storage indication method. When we use default storage indication here, there's our red warning, which is what I'm looking at. And this is telling us that this lower pond, that the water surface elevation there is exceeding the outlet device coming into it, and that there's an unhandled tailwater condition. And so in order to manage that, we would go to our calculation settings and change to dynamic storage indication method and click OK, and that resolves the warning. So that's the basic procedure for catch basins. We can use the same technique of a control drag in order to make copies, and we can actually right-click and select Raise Lower, and we could lower this one by 0.2 feet. So we can lower an entire structure. So particularly when these are very similar, that's a much faster way to set them up than having to re-enter everything from scratch. So we can set up an entire chain of catch basins. And then typically there will also be a runoff area, additional runoff area that will be coming in at different points along the chain. You will find an article on our website that talks about catch basins and storm sewers, and in particular how you model the grate and overflow scenarios. But this is a basic idea of how that's handled. Okay, I think that completes a very full session for today. If you have any questions, please do feel free to email support@hydrocad.net, and we'll be glad to get back to you. This session is being recorded, and so we'll have it posted on our website a little later today, and so you'll be able to view that or others in your office who may be interested. Thank you very much for joining us. Have a great day, and I hope we'll see you at a future session. Thank you. Bye-bye.